to make a reference sheet, something that you'll keep handy and next to you for the whole rest of the semester. So first, let's start by going over our paper, and all of this right now that we're about to say, you can put on your reference sheet. So, starting kind of from the beginning, what does f of x tell you? F of x tells you the height or the y coordinate. F of x is the y coordinate. So that's the actual height and of the graph. And what does f prime of x tell you? So what's, you know? Yeah, the derivative, which is the slope. So f prime of x goes into slope. And yes, you're right, Simone. Derivative is slope. So that's what f of x tells you, and that's what f prime of x tells you. Now, what general information about the shape of a graph can you obtain by using the derivative? What general information about a graph can you get by using the derivative? So generally speaking, you use the derivative because, first of all, if the derivative is positive, you know the graph is going up. So if f prime of x is positive, then you know that your graph is going up. That's helpful. If f prime of x is equal to 0, then you know that you've reached a flat spot. You know, either a maximum or a minimum. And if f prime of x is negative, then you know that your graph is going down. That's just general information, but that's what we want to keep in our mind permanently. That this is the baseline concept that we're talking about, is just figuring out when a graph is going up, when a graph is going down, and whether or not you've achieved a maximum or a minimum. Because we'll definitely want to be looking for those special points on the graph, is the flat spots, the maximum or the minimum. Okay, and then how do you actually find the maximum or minimum of a graph? Generally speaking, to find a max or a min, what do? Yeah, set the equation equal to 0. Set what equal to 0? Yeah. Set the derivative f prime of x equal to 0. Solve for x, because that's going to tell you the flat spot. And then plug, I should make that 2. Plug those x's back into f of x, into f of x to get the actual coordinates. The coordinates of the maximum or the minimum. So it might feel kind of funny or backwards that in order to find a maximum minimum, the first function you want to look at is the derivative, not the original function. You're actually not looking at the original function first. First, you want to look at the derivative. Set that equal to 0, solve for x, and whatever values that you got out of solving the derivative equal to 0, those are the x values of the coordinate of the max min, and then you have to plug that x back into the function to find the y value of the coordinate of the max min. So that might feel a little different, that you're actually first focused on the derivative, then focused on the actual function. Right? That might feel backwards. Like, I don't know, maybe that doesn't go backwards at all. But I would typically think if I was going to work in order, I'd do everything with my function first and then do everything with my derivative. But not so. You deal with the derivative first to find the location of the flat spots, and then you plug those x values into the function to get the y coordinates, and then you have your actual location. So that's something that we'll be doing for the rest of the class, is finding flat spots on a graph. Okay, well, today is September 24th. We'll be starting off with section 2.5b. You can see the course of the whole next chunk of the syllabus leading up to your second test. So we'll do sections 2.5b and then 2.6 all the way through 2.10. And then we'll have a review day / catch-up day in case we fall a little behind. That's just a padding day. And then you'll have your next text. What else? We're starting on section 2.5b today, but first, I recommend you take out a lined sheet of paper. Let's make a reference sheet to contain all the key formulas we've come up with thus far. And did I tell you the past, present, future walk to go bar jump? Oh my gosh, this is going to put all of you in such a good mood. Here's your joke. Past, present, and future walked into a bar. It was tense. Yep. That's it. That's the whole joke. It was tense. Again, now why is that funny? Because past, present, future are all past tense, future tense, present tense. Yeah, but it was tense because why? What's about to happen? They're all going to get in a fight, right? Like in a bar fight. Anyone? Yeah? No? Okay. Well, that's the joke. I love the joke. All right, let's keep going. So, section 2.5a was about the power rule, the product rule, and the quotient rule. 2.5b is about a new rule called the chain rule. So the first thing I like to do is write up a formula sheet. So let's do that. What are all the formulas that we know thus far? Have this on a piece of paper called your formula sheet. So what do we know thus far? We know that if the, these markers are so bad. I might have to go find some other markers. I wonder if my blue markers are something better. So if your function is just a normal power function, then the derivative is nx to the n minus 1. We also know if your function is the logarithm of x, then the derivative is 1 over x. And we also know that if your function is e to the x, then the derivative is also e to the x. And we also know the product rule, so d dx of f of x times g of x is the derivative of the first times the second plus the derivative of the second times the first. That's the product rule. And then we have the quotient rule, which, however you memorized it, is O B high minus high B ho all over O. All right, that's just to get us started. Jot all that down on your formula sheet. I'm going to find some other markers. Oh boy, I really hope some of these will. Hey, that's dark. Oh, thank goodness, that one's dark. All right, so that's what we have so far. One other thing we might want to note is that when you do the power rule, you want to keep in mind that x to the, well, the square root of x is really x to the 1/2. And any x in the denominator actually has to be rewritten as a negative exponent. Does that cover everything? Are those all the things we have to keep in mind when we do all these derivatives? I think so. And while you're at it on that formula sheet, you should put down how to find a max or a minimum. You set f of prime of x equal to 0, solve for x, and then plug those x's back into the function to get the coordinates. And I think that covers concisely the skills that we've been looking at this far. Did Alexis get here? No. Did Allison get here? Okay. Okay. Yes. What's that? No. Yeah. A question from what? Oh, from the homework? Oh, okay. Well, good idea there, Efren. I'm sorry, Efren. Bata. Before we write down the next rule, what a great idea. I pulled this up and I almost forgot. Let's look at chapter 2.5a and see if anyone has any questions from that homework. So here's 2.5. Here it is, 2.5. 2.5a. Who has any questions from the 2.5a? Bata's getting us started with what one? 15? Okay. So here's number 15, folks. Oh, and actually, a couple of you emailed me questions of other problems from here they'd like to see. So, in fact, I think this is one of them. So, how do we do this derivative? It's the chain rule. And so the chain rule is ODI minus hi-ho all over O. So, I'm going to start right here. O, which is x to the fourth, d high. So the derivative of the top is 35 x to the fourth plus 16 x cubed plus 9 x squared. Then minus, so that's it so far. There's ho d high. I wrote down ho, the bottom one, and then the derivative of the high, the numerator. Then minus high, so I write down exactly what I have. 7x to the fifth plus 4x to the fourth plus 3x cubed. D ho, and the derivative of the bottom is 4x cubed. All over ho ho, which is x to the fourth squared. Now, I'd just like to point out that for some of you, I think that you did that correctly. I think you did it correctly. I think you had all the right everything, your exponents, your coefficients. But then when you typed it in, I don't think you had enough parentheses. So notice, I'm going to do a parenthesis just to start my numerator. And then I'll do a parenthesis around x to the fourth, another parenthesis around the whole chunk, 35 x to the fourth plus 16 x cubed plus 9x squared, parenthesis. And then I'm going to do a minus, and then I'm going to do another parenthesis around the 7x to the fifth plus 4x to the fourth plus 3x cubed. And then another parenthesis around the 4x cubed. And then another parenthesis to close off the numerator, and then divide by a parenthesis to have parenthesis x to the fourth parenthesis to the power of 2 parenthesis. All right, now that's a whole lot of parentheses, but you'll notice now in my syntax, what I have typed in looks exactly like what I expected it to type in. So for all of you, when you're doing your homework and you're typing things in, look at the preview that they give you and make sure that that looks exactly like what you expected it to look like. Because I think you can all see now that the way it's typed into the computer is exactly what I have typed in here. I have a numerator and I have a denominator, and it's exactly the same. So I think you just needed more parentheses. If it's not the parentheses, then that means that some part of your derivative was incorrect. So let me hit submit, and it took it. So it did take that. I didn't even have to reduce it or anything. Okay, Bata, does that respond to your question?
Oh, yes.
The parentheses, okay. Another question from 2.5a. Yeah? 14, Cydia? 14. Oh, goody, great. Thank you for asking this one. So this is a product rule, not a quotient rule. Notice the first thing I did is wrap the e to the x in parentheses. That calls my mind to the fact that this is my first one, this is my second one. So I've got my first function, second function. So the derivative of a product is the derivative of the first, which is 4x plus 5, times the second, plus the derivative of the second, which is still e to the x, times the first, which is 2x squared plus 5. Now, if that's how you left your answer, you get full credit. I'm not going to type that in just now because I am going to simplify it. But if you typed that in, just like that, you would get full credit. But what are we going to do? What's a good best practice anytime you're dealing with e to the x? Yeah, factor out that e to the x. So if I factor the e to the x out front, then that leaves me behind with 4x plus 5 plus 2x squared plus 5x plus 5. And then I can actually combine those terms really nicely and easily. So now it's e to the x times what? 2x squared plus 9x plus 10. Now, I'll give you a couple of feedbacks for what I saw from you on email. Is again, wrap that e to the x in parentheses. Because I think I saw one person just type e. And it's not just e, it's e to the power of x. And furthermore, you wouldn't want to just do e to the power of x and then start typing in the next part, 2x squared plus 9x plus 10, you'd want to still wrap that e to the x in parentheses as well. Okay, so you see that, how I did that? Every individual component should go within parentheses. Parentheses are the language of computers. You need those parentheses there, otherwise it might mess up the whole problem. For instance, just to mess around with it here, if I got rid of the parentheses, well, it still works. In that case, it still works. You don't need the parentheses on the e to the x, but I still recommend that you do it, because what if you didn't and you just had the 2x without parentheses and then this? Oh, okay, that still works. But again, you're playing with fire. You should use parentheses around everything. Keep the parentheses and type it in with parentheses. Okay, so did that answer your question? Okay, great question so far. One more question. Number 12, thank you, Michelle. 12. So product rule for these two, you could theoretically FOIL that out first if you wanted to, but you don't need to. And it's best just to do the product rule just as it is. So there it is. My product rule now, again, is derivative of the first times the second plus derivative of the second times the first. So the derivative of the first is negative 24x to the fifth minus 30x squared times the second, which is 6 e to the x minus 3, plus the derivative of the second, now this one, what's the derivative of 6 e to the x? Still 6 e to the x, because the derivative of the e to the x is e to the x, and 6 is a coefficient which comes along for the ride. And what's the derivative of 3? 0, just nothing. So that gives us derivative of the second, which is 6 e to the x, times the first, which is negative 4 x to the 6 minus 10x. Okay. Now again, you can just type it in just like that. If you type it in just like that with all of those parentheses, you're going to get it correct. If you did want to simplify it out, it would be a little bit more labor because you'd have to FOIL this whole expression, first, outer, inner, last. I don't think any of us want to do that because then you'd also have to distribute this. I think it just ends up becoming a little bit more work than it's really worth. And so I think we could just leave it like that. I don't believe I took off credit on anyone's test if you didn't simplify an expression. If I did take out points on your test for not simplifying it, then come tell me and I'll give you the points back. Because my main concern is that you know how to do the product rule. Okay, thank you, Cheryl. Other questions? Okay, well, those were good questions. Bata, thanks for reminding me to take questions on the homework. Now let's look at the chain rule. The chain rule is a special final formula that we need to be familiar with. And this special final formula is built around the idea of function composition. So first, let's all just remember how function composition works. So everybody start by just making yourself a note about function composition. So let's say that I had the function f of x equals x squared plus 3. And I also have the function g of x equals, say, 5x minus 7. So everybody write that down. This is your example to remind everybody what function composition is. So my first question for you is, what is, and let's review the notation, f circle g of x? So maybe you remember this little circle here. It's a circle. It's not a dot. A dot means multiplication. A circle means composition. And the definition of this thing is actually f of g of x. So it means you're plugging the g of x function into the f of x function. So now let's look at how to do that. I have a particular way of doing compositions where I start by writing the f function really big and empty. So my f function is something squared plus 3. I'm going to write down something squared plus 3. So does everyone agree that that's the f function? That function is x squared plus 3, but I'm going to write it as something squared plus 3. Now what do I plug into the f function? G of x. So I plug in 5x minus 7 into the big parenthesis where it was. So that right there is the function composition of f of x of g of, f of g of x. And if you would all now, please kind of label this. The 5x minus 7, we're going to call the inside function. And then the something squared plus 3, we're going to call the outside function. I hope the way that's labeled just makes sense. That the 5x minus 7 is the inside function because that's what you put inside. And then the something squared plus 3 is the outside function because that's what you're plugging the inside function into. Did everyone write that down on a sheet of line paper? It's very important. We're clarifying our terminology right now. So how would this be different if we did G circle f of x? Are we about to get the same answer? We're not about to get the same answer. We're about to get something very different. And by the way, just to clarify what this is, we'd have to FOIL it out. So that's 5x minus 7 times 5x minus 7 plus 3, which would actually give us 25x squared minus 70x plus 49 plus 3, which is really 25x squared minus 70x plus 52. So just so we all know for the record, f of g of x is actually equal to 25x squared minus 70x plus 52. So now let's do g of f of x. So now that's really, by definition, g of f of x. So now we take the g function and we plug f of x into the g function. So again, what I do is I take my g function and I write it really big and I write it empty. So my g function is 5 something minus 7. I write down 5 something minus 7. That's the g function. 5 something minus 7. And then what am I plugging into the g function? The f function, which is x squared plus 3. And again, I'd like us to notate now that x squared plus 3 is the inside function because it's what we put inside of the other function. And we're calling g of x now, the whole thing is the outside function. It's really important that we're able to look at a function and be able to just visually recognize which part is inside and what part is outside. Almost always, the part inside is going to be something inside a parenthesis. So if you can notice something inside of a parenthesis, that's probably the inside function, and the rest of it is probably the outside function. Okay, so what does that actually equal? That's just distribute, and that's just 5x squared plus 15 minus 7, which is 5x squared plus 8. So in general, is f of g of x equal to g of f of x? In general, no. Generally, you should expect to get different things. Okay, well, that's just function composition. The chain rule is about taking the derivative of a function composition. Because notice, we have these basic derivatives that we're able to do. We can do basic derivatives, power rule, natural logarithm, and e to the x. And then we were trying to figure out how do you take the derivative of something more complex? Like how do you take the derivative of 2 functions being multiplied? Or how do you take the derivative of 2 functions being divided? And so now we're going to say, how do you take the derivative of 2 functions being composed? What if you take the composition of 2 functions? How do you take the derivative of that? So let's write down the formula for the chain rule. I'm going to put it down over here so it's nice and tall and up high. We're going to write it down and write it in English. So this still goes on your sheet of line paper right below all this function composition business. So given a function f of g of x. So we're given some function composition. The derivative is, so I'm going to write d dx of f of g of x. And I would say any formula that you learn in calculus, the important thing is being able to verbalize it. So notice how we're going to verbalize this. I'm going to write down the formula and I'll write it down in English. So the derivative of f of g of x is, oh, and by the way, which one's the inside function? G of x is the inside function. Which one's the outside function? F. Does everyone agree on that? That's very important. Okay, so the derivative of a function composition is the derivative of the outside function. The derivative of the outside function. Leave the inside alone. So far, the derivative of the outside function, leave the inside function alone, times the derivative of the inside function. That's the chain rule. That's how you take the derivative of a function composition. And now let's write it down in English. The derivative of the outside, leave the inside alone, times the derivative of the inside. And we'll go ahead and put it over here, just so it's all in the same spot. And everybody, just so we're clear, I made that dot really big. It's multiplication. That's not function composition. That's just regular multiplication. So it's f prime of g of x times g prime of x. Okay, is everyone really excited to do function composition? I'm sure you are. So to do our example, I'm going to do an example using the first one that we did, f of g of x. The example we're going to do is taking the derivative of this function. So, the derivative of the outside function. In that case, that means the outside function is the black function, the one written in black. The derivative of something squared. In fact, everybody, you might as well just consider this again as x squared plus 3. What would the derivative of x squared plus 3 be? The derivative of x squared is 2x, and the derivative of 3 is 0. Nothing. Yeah, 0. Okay, so the derivative of the outside function, so the derivative of the outside would be 2 times the something, and there's no longer a 3 there. So that's the derivative of the outside function. X squared plus 3 just becomes 2x. So something squared plus 3 just becomes 2 something. And the rule says take the derivative of the outside function, leave the inside function alone, and then multiply by the derivative of the inside function. What's the derivative of 5x minus 7? 5. Just 5. Okay, that's our first chain rule. We took the derivative of the outside function, leaving the inside function alone, and then you multiplied by the derivative of the inside function. Now, that can actually be simplified quite a bit, right? Even though formally that's the derivative of the outside, leave the inside alone, times the derivative of the inside. And I suppose I could have put that 5 in blue. That helps, because that's now the derivative of the inside function. How do we simplify that? You've got a 2 times a 5, so that's 10. So you have 10 times 5x minus 7, which is really 50x minus 7. Did I do that correctly? Does everyone agree that it's 50x minus 70? Okay, well, that's what the chain rule told us. Now you might say, are we right? Are we correct? Did that actually give us the right answer? Well, we can actually check, because we already found out what the composition of this function was. the composition was actually 25x squared minus 70x plus 52. What's the derivative of this? The derivative of 25x squared is 50x, and the derivative of negative 70x? The derivative of 52? Did we get the same answer? We did actually get the same answer. So the chain rule worked. The chain rule worked, and what's so cool about the chain rule is that you got to do the derivative as it was. And you didn't have to do what? All that nasty computation of the foiling. You didn't have to do all the foiling or anything else. You didn't even have to calculate the composition. You could just do the derivative of the composition directly. So that's the benefit of the chain rule. Yes, Bata?
What we suppose the 3x square instead of 3 and 3x square. So we use this as outside.
What are you talking about?
Instead of 5x minus 7 the whole square plus 3, then 5x minus 7 the whole square plus 3x square. So
you're wanting me to write down what? 5x minus 7.
yes.
And then what?
Plus 3x. Yes. So
But where would the 3x come from?
um,
The derivative of 3 is not 3x. The derivative of 3 is 0. Is that what you're saying? I don't know where you're getting.
so this one is not the original equation. 5x minus 7 plus 3.
No, the original equation is either x squared plus 3 or
Oh.
5x minus 7.
Well, that's
Oh, okay, no. Did I answer your question?
oh yeah.
Okay, okay. All right, so folks, that's the chain rule. This is all on your line sheet of paper, right? So now we all have the formula written down on a line sheet of paper. You all have an example written on your line sheet of paper. So now let's go ahead and proceed and look at our notes for chapter 2.5b, and let's try these problems out. Now, to be fair, this very first question, we're going to save that one to do after we've done quite a few examples and we feel more confident about the chain rule. And then we'll come back and look at number 1. So let's do number 2. Use the chain rule to find the derivative of 3 negative 8x cubed minus 5x to the 8th. Now, I'd like you all, if you have colored pencils, that would be great. If you don't have colored pencils, I'd like you to at least notate which is the inside function. Does that make sense in this problem that the negative 8x cubed minus 5x to the 8th is the inside function? And then the outside function, I want to make it painfully obvious. The inside function is negative 8x cubed minus 5x to the 8th. And the outside function is 3 something to the 18th. What is it? I would write that down if I were you, just to call your attention to it. The inside function is the little polynomial inside, and the outside function is 3 something to the 18th. And so we'd like to do the chain rule on this. And to do that, we're going to use this verbiage, take the derivative of the outside, leaving the inside alone, and then multiply it times the derivative of the inside. And as we do some examples, it will become more clear. So that was just the function. I just wrote it down. So now let's do the derivative. What's the derivative of the outside function? So folks, if you were just looking at this function right here, 3 something to the 18th, this is just a power rule. You'd multiply by the 18 and then subtract 1 from the 18. So first of all, what's 18 times 3? 54. So the derivative of the outside would be, I'm just going to write it down, 18 times 3 parenthesis to the 17th. Does everyone agree that's the derivative of the outside function? Leaving the inside function alone. So everyone agree that's the power rule of the outside function. I multiplied by the 18. I didn't write 54 yet because I wanted everyone to see that I multiplied by the 18 times the 3. I kept the inside alone and I subtracted 1 from the exponent. So that's the first step. Take the derivative of the outside function, leaving the inside alone, times the derivative of the inside function. And what's the derivative of the inside? Yeah, negative 24x squared minus 40x to the 7th. And so our final answer would just be 54 negative 8x cubed minus 5x to the 8th, 17 times negative 24 x squared minus 40 x to the 7th. It does not simplify very much. That's just the answer. Took the derivative of the outside function, leaving the inside alone, and then multiplied by the derivative of the inside function. And at that point, you look at the answer and you say, apparently that's the derivative. Apparently that's the formula for the derivative telling you the slope at every point on that function. So let's try that again. Everyone take a look at this next function. 2x plus 4 to the negative 3. The outside function is the something to the negative 3. The inside function is the 2x plus 4. Does that make sense, how we chunk that up? The inside function is naturally the thing inside the parentheses, the 2x plus 4. The outside function is something to the negative 3. So how do we do the derivative? First, we're going to take the derivative of the outside function. So if you just want to look at it in context, what would x to the negative 3 be? What would the derivative of that be? Would it be negative 3x to the negative 4? That's what the derivative of just x to the negative 3 would be. So now the derivative of the outside alone is going to be negative 3 times something to the negative 4. And we leave the inside alone. So you still have the 2x plus 4 inside of that. And then you multiply by the derivative of the inside. And the derivative of the inside is simply 2. Because the derivative of 2x is 2 and the derivative of 4 is nothing. So there you have it. The derivative of the outside function, leaving the inside alone, times the derivative of the inside function. Now, can that be simplified at all? Yeah, it can be simplified a lot, actually, because the negative 3 times the 2, negative 3 times 2 can be a single coefficient. That's really negative 6. And where does the 2x plus 4 go? Since it's being raised to the power of negative 4, the whole thing goes into the denominator, and you have 2x plus 4 to the 4. That's what your final answer would look like. Remember, anytime you have a negative exponent, you push that object into the denominator, so you have a positive exponent. And otherwise, the negative 3 times the 2 stays up top in the numerator. Are we done with that problem? What else do we have to do, Josue?
Find them.
Yeah, we actually also want f prime of 1. So simple enough, you just plug 1 into that. So f prime of 1 will be negative 6 over 2 times 1 plus 4 to the 4th, which is really negative 6 over 2 times 1 is 2, 2 plus 4 is 6, 6 to the 4th. And this actually simplifies pretty nicely. Before you even multiply 6 to the 4th, you can just write this as negative 6 over 6 times 6 times 6 times 6. And what are you going to do? You can cancel one of the 6's. So you're really left with negative 1 over 6 cubed, which is negative 1 over 216. Now remember, we're in a calculus class, so fractions always mean something. What does that fraction represent, since we're talking about f prime? We're talking about derivatives, so we're talking about slopes. That's the actual slope. That's the actual slope of that point on the graph. So if I was actually looking at this graph, and I went to the coordinate at 1, which if I plug 1 into all that, that's just barely right, like right there. There's my coordinate. And my slope is down 1, right 216. If I went down 1, right 216, that would be an incredibly shallow negative slope. Right? That's what this answer tells me. Negative 1 over 216 tells me that it is very shallow, but negative. So it's like you're barely walking downhill on that graph. Which, as always, a great idea would be to confirm your suspicion by going to Desmos and actually taking a look. Our function was 2x plus 4 to the power of negative 3. And what is our graph doing at x equals 1? It's barely going downhill, right? So it worked out. Our answer was correct. Okay, let's try a few more chain rules. Does anyone want to ask a question before we keep going? I'm nervous to keep going because, I don't know, I just haven't heard anyone from a little bit. Does anyone have any questions or anything you would like to ask about? Maybe it's just helpful to keep going through examples. All right, let's do the next one then. We want to take the derivative of 5e to the 2x to the 7th minus 2x to the 8th. What part of all that is the inside function? Yeah, the 2x to the 7th minus the 2x to the 8th. A good intuition is always to think whatever's inside the parenthesis is the inside function. So if you want to think about it in this particular problem, the outside function would be 5e to the something. Or really, you could think of it as 5e to the x. That's the outside function. And then the inside function is 2x to the 7th minus 2x to the 8th. So we have the inside function, we have the outside function. So how do we take the derivative? The chain rule states that you take the derivative of the outside function. Well, what was our outside function again? 5e to the x. What's the derivative of 5e to the x? 5e to the x. So the outside function stays the exact same, and the chain rule states take the derivative of the outside, leave the inside alone. So you just leave the 2x to the 7th in there, and then multiply by the derivative of the inside function. And in this case, the derivative of the inside function is what, 14x to the 6th minus 16x to the 7th? Yeah, that's it. That's the chain rule. And look at it again. The derivative of the outside function, the derivative of 5e to the x is still 5e to the x. We just wrote it down and we left the inside alone. And then we multiplied by the derivative of the inside function. Notice really carefully, folks, look at all of your own penmanship. This binomial had better be teeny, teeny, tiny and up above the e, whereas this binomial is normal sized. Right? So if I wanted to really exaggerate it, it would be 5e to the 2x to the 7th minus 2x to the 8th times 14x to the 6th minus 16x to the 7th. Right? So according to your handwriting, it should be very obvious which part of that is the exponent. Every once in a while, I see people write this like this. 5e to the 2x to the 7th minus 2x to the 8th times 14x to the 6th minus 16x to the 7th. Now, what does that look like? It looks like it's all up in the exponent. And that's not correct. It's not all up in the exponent. Just the exponent is the teeny tiny one. The part that you write out afterwards is normal size, just like the 5. And then technically, the 5 can combine with that part. So we can now actually distribute the 5 to those numbers so that we really have e to the 2x to the 7th minus 2x to the 8th times, what would that be? 70x to the 6th minus 8x to the 7th. That would still be correct. Distributing the 5 over into that parenthesis. Not that you have to do that. The software will still accept your answer if you just have the 5 out front. So that's an example of doing the chain rule with an exponential function. Maybe y'all need another joke. What do you call a bee who can't make up his mind? What do you call a bee that can't make up his mind? Maybe. No? All right. Well, let's try the next one. We have a function which is the natural log of x squared plus 4x plus 5. What's the outside function? Natural log. And what's the inside function? X squared plus 4x plus 5. And so we want to take the derivative. This one's a little tricky. Remember, the outside function is just natural log of parenthesis, or better yet, you could say natural log of x. What's the derivative of the natural log? 1 over x. Now listen, folks, sometimes we call the part inside the natural logarithm the argument. So the natural log of the argument. The natural log of the argument, if you take the derivative, becomes 1 over the argument. So the natural log of an argument, the derivative of the natural log of an argument becomes 1 over the argument. So watch very closely here. The derivative of natural log of an argument becomes 1 over the argument. So the derivative of natural log is 1 over whatever was inside of it. And again, the chain rule says the derivative of the outside, leave the inside alone. So that's just the derivative of the natural log part. It just becomes 1 over x squared plus 4x plus 5. And then you multiply by the derivative of the inside. So the derivative of the inside, watch very closely how I do this. This is a fraction. I want to be clear that what I write next is in the numerator, times the derivative of x squared plus 4x plus 5 is 2x plus 4. I'm going to write 2x plus 4 over 1. Just to remind myself that that 2x plus 4 is up in the numerator position. Right, I'm just multiplying times 2x plus 4, but I want to be very careful to remind myself that that 2x plus 4, if it gets multiplied by this fraction, is going to get multiplied by the numerator, not the denominator. And in fact, then we would simplify all that, multiplying straight across and say the derivative is 2x plus 4 over x squared plus 4x plus 5. Notice what's so interesting about these two examples. When you take a derivative of e to the x is still in the derivative. So if you start with an e to the x function, you still have an e to the x function. But when you have a function that's a natural logarithm, when you take the derivative of the natural logarithm, you no longer have a natural logarithm. That's just interesting to note. So the derivative of e to the x is still e to the x. Your answer is still going to have e to the something. Whereas the derivative of a natural log, you end up with just a polynomial. The natural logarithm is no longer part of the answer. Would you say, oh yes, well, that's very interesting. Okay, let's see here. We have some more really good examples to do. And some good business examples. But right now we will stop, we will take a break. And we'll come back, and let's see, the time is 11:51. Everyone be back at 12:01. Everyone back at 12:01. Although, yeah. Okay. Ata?
Yes.
Did I answer your question from a while ago?
Yes.
Did I really? Okay. Efren, how's this? What's up? Is it making sense? What's right? You're wearing one of my favorite shirts.
Fine.
You have a graphing calculator?
Yeah.
A TI? Yeah, let me see it. Sweet. So, when you use a graphic calculator and you do any work at all, like 5 plus 6, you get that. Now let's say I want to take the square root of that. I can do the square root, and then instead of typing 11, I can do second answer. And it just brings that number and puts it there for me so I don't have to. Look at that. Sure. Nice, huh? Yeah. Yeah, what's that? Stephen, let's see that homework paper of yours.
These are considered your homework papers.
Yeah, were you talking about the practice test or the homework papers?
I'm just thinking of it, but I think it was just, I got like, I didn't know, like, I didn't see any marks down here, so I didn't know if this year.
Actually, I didn't mark anything on it, so that leads me to believe.
Maybe you're talking about the more homework.
Yes, I can look it up real quick.
I'm looking it up too. It's not like a competition. We can both look it up. But whoever finds it first obviously wins.
Alright, it's Grace.
What's your last name, Steven? Oh, yeah, there you are.
Davis.
No, it's just one parenthesis at the very beginning and one at the very end. So one more at the end. Yeah. Because see, that opening parenthesis is capturing everything, and then that closes it up.
And then was it the science chapters?
Your notes, you got full credit, practice test, full credit. It was just the more assignments.
Okay, that's probably because I haven't finished my one assignment yet.
Yeah.
Okay.
Okay, that answers the question.
That's perfect then. Perfect. That's my bad. I misconfused the assignments.
Yeah, no, it's fine. And I think you can still finish it if you still have a late pass.
Yes, I have 12 hours.
There you go.
So, thank you.
Have to clarify. I want you to be a satisfied customer.
I'm satisfied.
After all, you are all customers. Oh, another nice marker. Oh, another nice picture. That's good. Actually, all right, folks. Oh, let's keep going. So, moving on to number 6. We're gonna hold off on 6, and we'll go back and do number 1, then number 6. Let's look at. Actually, we might be able to do all these in order. Yeah, let's go on to 8 and 9. I want to finish doing some traditional examples before we go into some more conceptual, interpretive results.
What about number 7?
We're going back to that one as well. 1, 6, and 7 we'll go back to in order. So number 8. What's our inside function? What's our outside function? There's no parentheses per se, but perhaps you still see that there's an obvious inside function. What are you inside of? The square root. So what we have here is the outside function is the square root. The inside function is the 2x squared plus 3x plus 7. Now, how do we actually write a square root? Because we don't actually we never take the derivative of a square root. We take the derivative of to the power of 1/2. So what we really have here is that f of x is something to the 1/2. That's the outside function. And then 2x squared plus 3x plus 7. So that's what we want to take the derivative of. And I hope that inside is obvious and the outside is obvious. So what is the derivative of something to the 1/2? If I have something to the 1/2, the derivative is 1/2 times something to the, we have to do 1/2 minus 1, right? And minusing 1, you might as well do minus 2/2, so that's negative 1/2. So is that the derivative of something to the 1/2? 1/2 times the something to the power of negative 1/2. So let's do the chain rule. The derivative of the outside, it's down f prime of x. The derivative of the outside is 1/2, bring it down up front, to the power of 1/2 minus 1, which is really 1/2 minus 2/2, that's negative 1/2. So that's the derivative of the outside, leaving the inside alone. And then you multiply it by the derivative of the inside function. So everything I just did right there is just taking the derivative of the outside function, leaving the inside alone. Now we multiply by the derivative of the inside function, which is what? Just 4x plus 3? Okay, so that's the chain rule. Now it's just a matter of cleaning it up. We can clean that up considerably. So for instance, anytime you have an exponent that is negative, what do? You take this whole thing and push it into the denominator. So now what we really have, and let's be very careful now, we're going to end up with a big fraction. Let's look at our first fraction, 1/2. A 1 goes in the top, a 2 goes in the bottom. Right? Because 1/2, naturally, the 1 stays up top and the 2 goes down to the bottom. This whole term, 2x squared plus 3x plus 7 to the negative 1/2, goes to the bottom. So 2x squared plus 3x plus 7 to the positive 1/2 now, since we pushed it. And then what about this last term, 4x plus 3? Does it go in the numerator or the denominator? That's in the numerator. Technically, that's 4x plus 3 over 1, so the 4x plus 3 stays up top. So I hope you see how we took all those parts and pieces and shoved them into one big fraction. Again, the 1 stays in the numerator, the 2 stays in the denominator. This whole term goes into the denominator because of a negative exponent. And the 4x plus 3 was technically over a 1, so that stays in the numerator. So now we take all that, and this we can still clean up by writing it down as, the numerator is just 4x plus 3, and the denominator is 2 times the square root of 2x squared plus 3x plus 7. And that's the derivative. Notice, again, if you want to think big picture about these derivatives, when we take the derivative of a 5e to the x or an e to the x, your answer still has an e to the x. If you take the derivative of natural log, your answer no longer has a natural log. And when you take a derivative of a square root, what do you notice? Where does that square root go? Into the denominator. Yes, into the denominator. So when you take the derivative of a square root, the square root stays in the problem, but it's no longer in the numerator, it's in the denominator. Okay. Yes, Sila?
I don't understand why you have your, so f5 of x, where it's 1/2 at the front, and then minus the negative exponent.
You just asked about these two parts right here? Well, when you first start, you have this as the derivative. So when you take the derivative of a power, See, I did it over here as an example. Let's just say that you had x to the 1/2. Let's do that derivative. So you multiply by the 1/2, right? So that becomes 1/2 times x, and then you subtract 1. But how do you subtract 1? You call that 2/2. Because 2/2 is still 1. And so 1/2 minus 2/2 is? Wait, Celia, did that answer your question?
Yeah.
It did? Okay, yeah, and so we did the exact same thing here. Okay. Okay, well, folks, the next problem is identical. We still just have a function with a big square root. The only difference is we have a coefficient out front. What do coefficients do when you take the derivative? They just come along for the ride. Nothing's going to happen to the 8. The 8's in the original, the 8's going to be in the derivative as well. So let's start by rewriting. So this is really f of x equals 8 times 5x cubed plus 3x to the 8th to the 1/2. And our inside function is 5x cubed plus 3x to the 8th. And our outside function is 8 something to the 1/2. I want everyone to see that clearly. The outside function is 8 something to the 1/2. And the inside function is 5x cubed plus 3x to the 8th. Is that fair? It's really helpful to bring your attention to what the actual outside function is and what the actual inside function is. Because technically, we're going to take the derivative of both of these. So I like to take the derivative of the outside function first, just to remind myself what the answer would be. If I simply had 8x to the 1/2, what is my derivative going to be? 4x to the negative 1/2? Does everyone agree? So that's helpful. That's nice to look at that ahead of time and just know that's the derivative of the outside function. What about the derivative of my inside function? That's just going to be 15x squared plus 24x to the 7th, right? I would just look at all this and call it scratch work. That's just scratch work. Because now, already having it written down, it should be very easy to come over here and say, okay, the derivative of the outside function would be 1/2 times 8 is 4 to the negative 1/2. Leave the inside alone. And then multiply by the derivative of the inside, which is 15x squared plus 24x to the 7th. Is that the answer you expected? The derivative of the outside, leave the inside alone, times the derivative of the inside. Did we do that right? Okay. Okay, now again, we have to clean that up. We clean that up by making a very obvious big fraction, and we put everything into the numerator or denominator, respectively. So where does the 4 go? Numerator or denominator? Numerator, because that's really 4 over 1. So I got a 4 in my numerator. Where does the 5x equals 3x to the 8th to the negative 1/2 go? Into the denominator, and I know that that's to the power of 1/2, so I'll just go ahead and make that the square root of 5x cubed plus 3x to the 8th. And where does my 15x squared plus 24x to the 7th go? Technically into the numerator. So that's now 4 times 15x squared plus 24x to the 7th. That's pretty clean as far as answers go. That's pretty clean. What's the last thing we could do if we wanted to? We probably could just distribute that 4 in, just to get rid of the 4 so it's not there. So that could be 60x squared plus 4 times 24 is 80, 96 x to the 7th all over the square root of 5x cubed plus 3x to the 8. There. So that's a pretty clean answer in terms of final form. Again, you'll notice when you take the derivative of a function with a square root in it, the square root still is in the answer. It just moved to the denominator. So that way we can check and see that we got it. Or at least we know part of it by expectation. Okay, I've got 3 more problems to do with you. And these next 3 are going to be more basic again. These were tricky because it was square roots and natural logs and exponentials. But hopefully these next few or an easier, these next two are a simpler review. So I'd like to have everyone try the next two on their own. So everybody go ahead and, if you want to write it down once in your own handwriting, do the chain rule on that, and then do the chain rule on this. And remember to follow the steps exactly, just like the verbiage. Take the derivative of the outside, leaving the inside alone, and then times the derivative of the inside. So give it a shot, and I'm just going to walk around and help out. Nice, good. What's that? The outside is definitely something to the negative. Yep, that's it. That's right. Yep. So that's a negative one. Cool, negative. So then when you multiply that up front, you have a negative one. And then times this is a negative 2, and then multiply by the derivative. There you go. The inside is just.
Wait, the derivative. Okay.
There you go. That's it. Hey, very nice. That's it. I haven't finished walking around the room yet, but everybody, just so you can check your answer for the first one, you take the derivative of the outside, which means you bring down the negative 1, you subtract 1, and you keep the inside alone, and then you multiply by the derivative of the inside, which is just 3. So if that's what you have written down, that's fine. That's the answer. However, you could go ahead and put everything into the numerator and denominator where it belongs. So the negative 1 would stay in the numerator, the 3x plus 7 would go into the denominator, and the 3 would also stay in the numerator, and you end up with negative 3 over 3x plus 7 squared. You do not have to FOIL out the 3x plus 7. That's fine. It's just 3x plus 7 squared. Okay, keep going. Try the next one. That's fine. That's fine. All right, let's check answers on the second one. The second one, again, we take the derivative of the outside. So that the derivative of something cubed would just be 3 something squared, leaving the inside alone, x squared plus 5x plus 7. And then multiply by the derivative of the inside. The derivative of x squared plus 5x plus 7 is 2x plus 5. Now you'll notice that in this one, there's no numerator denominator, right? Everything is a positive exponent. So that's just it. That's your answer. You definitely don't have to FOIL this out, and you definitely don't have to multiply it times the 2x plus 5. You're just done. Now, there's one more step I didn't do. I just wanted to check to make sure we got the derivatives correct. I still need to go back and find f prime of 5, and I still have to go back and find f prime of 3. and then interpret it. What does that mean? You all know that whatever you calculate for f prime of 5, it's going to be a slope. And whatever you get for f prime of 3, that's a slope. So now I'm going to go ahead and plug in f prime of 5, and that's going to be negative 3 over 3 times 5 is 15 plus 7 is 22 squared. Well, my goodness, negative 3 over 22 squared. That's a lot. Not sure what that is. Negative 3 over 242. What kind of a slope is that? Very, very negative and shallow. Down 3, right 242. It's a very gradual negative slope. Oh, nope, I did that wrong. It's not 242. 44, thank you. Silly. Okay, and then how about the next one? F prime of 3. Got to plug 3 into all that. F prime of 3. So that'd be 3 times 9 plus 15 plus 7 is 31 squared times 2 times 3 is 6 plus 5 is 11. No idea what that is, but it's a gigantic number. Okay, not that gigantic. How big is that number? It's just 3 times 31 times 31 times 11. Did anyone? 3 times 31 times 31 times 11. Did anyone else get 31,713? 31,713? Someone else did get that? Okay. So what does that mean? That's also a slope. 31,713 over 1. So that means you're going up 31,000, right 1. Up 31,000, right 1. That is incredibly steep. I mean, that's darn near a vertical line. That's how steep that function is at 3. Okay. Well, number 12. This is fun. Number 12, and then we have some word problems. Number 12 is a quotient rule inside a chain rule. Oh, is everybody excited just to think about it? This is exciting. It's a quotient rule inside a chain rule. Oh my goodness. I know everyone's on the edge of their seat. Your mouths are watering. You're like, wow, let's do this problem. So let's try it. We've got f of x equals x plus 1 over x plus 2 to the 5th. First of all, what's the outside function? Something to the 5th. Very nice. Something to the 5th. That's my outside function. And again, if you wanted to think ahead of time what everything is, the outside function is something to the 5th, and therefore the derivative of that is 5 something to the 4th. I'm just planning ahead what the derivative of the outside function is going to be. And my inside function is x plus 1 over x plus 2, and I can plan ahead what that derivative is going to be. That's going to be ho d high minus high d ho all over ho ho, which is going to work out to be x plus 2 minus x minus 1 over x plus 2 squared, which those x's cancel out, and it's just 1 over x plus 2 squared. Okay, so I did a lot of front work. Right, I was just planning out. I'm just planning ahead. I know I've got my outside function, and the derivative of which is 5 something to the 4th. I got my inside function. I went ahead and did the quotient rule just to see what I would get. So now with that advanced planning, now I'm going to go back and do the chain rule. Does anyone like this idea of doing the derivatives ahead of time?
Yeah.
I mean, I kind of like the idea because then the work is done and you just have to copy it down. So maybe I'll wait one more second while you do that, if you were. And by the way, does everyone agree with my quotient rule? I did that kind of fast. I might have made a mistake.
So when x plus 1 over x plus 2 is in parentheses, you need to do the quotient rule before you do anything else, correct?
Well, right. Well, because now, let's do the chain rule, and hopefully that answers your question. The chain rule now is the derivative of the outside, which is 5 something to the 4th, that's the derivative of the outside, leaving the inside alone, which is still x plus 1 over x plus 2, times the derivative of the inside. And so now, because I already did the derivative of the inside, my quotient rule, I can just go ahead and write down 1 over x plus 2 squared.
Oh, okay. So yeah, you would.
I just found it helpful to do it ahead.
Yeah, no, absolutely not. No, I understand what you
Okay. So, yeah, front work. I don't know if you've ever heard the word front work. I don't know if I'm just making that up. But I'm calling this my front work. I'm doing it up front. Just getting that work out of the way so that then when I go to do the chain rule, it's just a matter of writing everything down instead of trying to do it all on the fly. Now, can that be simplified? You might look at that and say, no, that really can't be simplified. And yes and no. I have to admit, part of this class is not just the calculus. It's also learning advanced techniques for algebraic simplification. Doesn't that sound awesome? If that was the name of the class, would you have taken it? Advanced techniques for algebraic simplification. That doesn't sound too attractive. But it is, so watch. This problem right here, this is really 5 over 1. This is really x plus 1 to the 4th over x plus 2 to the 4th. And then that's 1 over x plus 2 squared. Oops, the 4th. Does everyone see what I just did right there? All I did was just write 5 as a fraction. And then I took my x plus 1 over x plus 2 to the 4th and I broke it up into x plus 1 to the 4th in the numerator and x plus 2 to the 4th in the denominator. I don't know if you knew that you're allowed to do that, but you can. And that's part of this course, Advanced Techniques in Algebraic Simplification. And then you have the 1 over the x plus 2 squared. Now do you see what we can do? Yeah, now it's a little more obvious that we can go ahead and leave the 5x plus 1 to the 4th in the numerator. And what do we have in the denominator?
X plus 2 to the 6th.
Yeah, very good, x plus 2 to the 6th. And that's just a little more clean. It's just a little more clean as far as an answer goes. Hey, Matt Jolly.
Hello, JW.
How's it going?
I like the idea of doing the derivatives first.
Do you?
Yes.
I knew it, folks. And you're an English major, right?
I am, yeah.
Fantastic. Look at that, folks. Thanks, Matt. Now, do you think he really knew what he was talking about? Or did he just say, yeah, do the derivatives first? Anyone want to take a vote? I'm going to go ask him later. He said, did you really know what you were talking about? Or did you just hear the phrase, do the derivatives first, and you just said it? Because I would totally mess with his English class, too. I'd be like, yeah, diagram that gerund clause. Whatever that means, I don't know. I'm not an English guy. Okay, well, everyone, we're done. What's the other thing we have to do? No, that's it. It's just f prime of x. There's our derivative. All right, so now let's do a couple word problems. Yeah, let's do the word problems. And then we'll go back and look at those more conceptual problems. So here we are, number 13. Now, I'm just looking at the formula in here. Do you see a chain rule in here? Do you see an inside function and an outside function? I don't immediately see how this is an example of an outside function and an inside function. That just looks like a polynomial. So let's read the problem and see what it's talking about. Suppose a product's revenue function is given by that, where R of Q is dollars and Q is units sold. Okay, what's the first thing you do? We've only read one sentence so far. What's the first thing we do? Draw a graph. First thing we do is always draw a graph so we know what on earth we're talking about. What's the shape of this graph? It's a parabola that's upside down. So, whammo. We already know what we're talking about. We've got an upside down parabola. It has a maximum value. That's a flat spot. It has an x-intercept. We could type it into Desmos if you wanted to look at it. But it's going to be an upside down parabola that looks like that. So find a numeric value for the marginal revenue at 16 units and record your result in the box below. Okay, marginal revenue. So now is a great time for us to give this definition. Marginal revenue means the revenue of the 16th unit. Not the revenue from all 16 units, just the actual 16th unit. So let's make two columns on our paper. We're going to talk about marginal revenue both in terms of a pre-calculus definition and a calculus definition. In pre-calculus, before you do any calculus, if you wanted the marginal revenue of just the 16th item, you would say the revenue of 16 objects minus the revenue of the first 15 objects. That's the definition of the marginal revenue of just the 16th object. Because you're taking the revenue of all 16 things, subtracting the revenue of just the first 15 things, and that's giving you the revenue that you acquired from the 16th object. So how do we calculate all that? We have to actually plug those numbers in and get them. So you would use your calculator, and you do -8 16 squared plus 716. And you get one value, 9152. And then you would do the exact same function, but you'd plug in, you'd plug in 15. And you get 8700. And you subtract them. And apparently the revenue from the 16th item was $452. All of that is calculator work and very basic. We didn't do any calculus just then. We were just saying, again, remember the marginal revenue at 16 units means find the revenue from the 16th unit exactly. You do R16 minus R15 and that's it. Now the calculus method, marginal revenue is defined to be, I'll write it down for you. Marginal equals the derivative. So if I want the marginal revenue of the 16th unit, it's simply R prime of 16. That is the marginal revenue at the 16th unit. So that's your pre-calculus method versus your calculus method. In pre-calculus, you have to calculate two different revenues and subtract them. In calculus, you just take the derivative of the revenue function and plug in 16, and that's telling you approximately how much revenue you got from the 16th item. So let's go ahead and first calculate R prime of Q. What's the derivative? Negative 16Q plus 700. And so R prime of 16 would be 444. Now I want you to notice these two answers. The pre-calculus method is exact, whereas the 444 is approximate. There's a little irony here. You would think that a calculus method would be even better. But in fact, the calculus method is only giving you the approximation to the answer. It's only better because it was easier to do. It's easy to take the derivative of this, and it's easy to plug a number into a linear function. It's harder to plug 16 into that function, and then 15 into that function, and then subtract. So the pre-calculus method takes more time, and the answer is exact. The calculus method takes less time, and the answer is approximate. So which one would you rather do? The what? The calculus method? Because it would be faster and it's an approximation. Yeah. So it's an approximate, it's faster. Whereas this is exact and takes more effort. So now that you've seen both of them, I would maybe make a note that marginal revenue is at, whatever, like say the 16th unit, is exactly equal to R of 16 minus R of 15, but only approximately equal to R prime of 15. I'm sorry, R prime of 16. All right, so it's important that you see that approximation symbol there. If you want the exact marginal revenue, you calculate both and subtract. If you just want the approximate marginal revenue, you just take the derivative and plug in 16. What did we just find out? What does marginal revenue mean anyway? Not the price.
The revenue.
The revenue, how much money you just made from the 16th object. That's what we're interested in, is how much money you made from the 16th object. So take a look. If I go in here now and we do the revenue function, negative 8 times x squared plus 700x, that's my revenue function. There we go. It's a parabola. Boy, a very tall and skinny parabola, my goodness. Oh man, it goes all the way up to 16,000. Let me make a better thing here. 0 to, what, maybe 30. Oh, no, I'll go further than that. 60, further than that. 100. There we go. So there's our revenue function. It means that as I start selling objects, I make more and more money. But what happens? There's a point at which if I sell more objects, what's happening to my total revenue? It starts going down, right? That's called the point of diminishing returns. Don't keep selling objects, your revenue is going down. And if I sold 87, no. What's that number? If I sold 87.5 units, I'd actually make no money. So you have no motivation to sell that many. How many should you sell? 43.75 units. Because that's going to maximize your revenue. So when we did the derivative, which was actually negative 16x plus 700. Whoops, that's an x. There we go. Now my derivative, notice, now the blue line is telling me how much money I'm making from each object. So this object, this is how much money I'm making. And you'll notice that by the time I get to the 43rd or so object, I make, hold on, 0 money off of that object. So I wouldn't want to sell the 43rd.75 object because I didn't make any money from it. Where do I want to sell objects? Only over here. Because this is where I'm actually making revenue off of each object. Okay, well anyway, that's what we're talking about with marginal revenue. Let's try another one. I think this is going to be the same question. Suppose the product's revenue function is given by that. Find an expression for the marginal revenue. Simplify it, record your answer in the box below. Oh, well that's it. How do you use calculus to find the marginal revenue? You just take the derivative. So this was a very simple question. They're just saying find an expression for marginal revenue. So everyone, you write it down as MR of Q, that's marginal revenue of Q, is R prime of Q, which in this case is just negative 10Q plus 400. Right, is that it? So there, that's just a nice little concise statement of what we know. The calculus technique for finding the marginal revenue is just the derivative of revenue, which is that. Okay, well that was a simple one. Okay, last big question, then we'll go back and do number 1, 6, and 7. What's that, Walter? What was the answer for number 14? This is. Suppose the product's revenue function is given by that. Find an expression for the marginal revenue. That's it. Simplify and record your answer in the box. Marginal revenue is just the derivative of revenue. And marginal revenue is telling you the revenue from that object, not all the objects, just that object. That's the difference between marginal object or marginal revenue and revenue. Revenue means, RQ means revenue from everything, revenue from all objects, whereas R prime of Q is the revenue from that object. Okay, does that help? The difference? Okay. Mata, does that answer your question? All right.
So the R prime is
negative 10? R prime is negative 10Q plus 400.
Yes. What is the final answer?
No, that is the final answer. They were just asking for an equation. They didn't ask for the revenue from any particular object. They just said, in general, find the expression for the marginal revenue function. That's the marginal revenue function. So let's just say about that you did want to find the marginal revenue for the 16th object. Then you would plug in 16 and get negative 10 times 16 plus 400, which would be negative 160 plus 400, which would be 240. Which means the 16th object got $240 in revenue. Okay, did that answer your question? Okay. Okay, folks, last good meaty question here. We have the function p of x equals that, and it gives the profit when some number of units are sold. What's the first thing we should do? Graph it. Graph it. So everybody make yourself a nice graph right here. Just to be accurate, we better plug it into Desmos and see what it looks like. So that's Negative 2.5 x squared. Is that 875? Yes. Minus 8.5. Now, folks, you'll notice when you graph something on Desmos or your graphing calculator, what do you have to do for the first couple minutes? Just adjust your window to find a good window that shows you the whole thing. So here's our whole parabola. I can already take a sneak peek that the maximum profit occurs if I sell 175 objects. So let's make our graph. The maximum profit is when I sell 175 objects. I'm cheating right now, right? I'm looking at the graph. And my profit is going to be $68,062.50. So by looking at the graph, we're getting all the information that we're going to use calculus to get. I also know my x-intercepts are at 10 and 340. Why do we look at a graph and write down all these things ahead of time? So we know if we got the right answer. Because now we're about to do calculus to get all the answers that the graph gave us already. So let's go ahead and give it a try. Find the profit when 90 units are sold. How do we find that? How do you find the profit of all 90 units? You just plug it in. P of 90 equals. So you would take your calculator, negative 2.5 times 90 squared, plus 875 times 90 minus 8,500. And if you do all that on your calculator, we would get 50,000. Does that look reasonable from our graph? 90 would be about here, and that would put us around here, which is 50,000. Does that answer look relatively correct? Compared to what we already knew? Yeah, it looks pretty good. Put your answer on the graph. You have a graph already. Put your answer of 90 and 50,000. You'll notice that your answer for 90, that dot is just barely lower than that dot, and it went from 68,000 down to 50,000. So that's all very reasonable. And if I really wanted to, I could just come over here to my graph on Desmos and graph a vertical line at x equals 90. And then I can see the intersection point, which was at 90, 50,000. So sure enough, that worked. How about the average profit per unit when 90 units are sold? What on earth does that mean? What's average profit? How do you calculate average profit? Yeah, you take your total amount of profit and divide by the number of objects, right? So the total number of profit was 50,000, and the total number of objects we sold was 90, and therefore the average profit per item is 5 by 5.5 repeating. I tell you what, I like this job. I wish I could make something at home that every time I sold it, I made $550 in profit. I would definitely just stay home and do that. Unless it took me a week to build one, then that's probably not a good business anymore. It's not much per week. Okay, so that's the average. How about the rate that profit is changing when 90 units are sold? What does that mean? The rate that profit is changing. Rate is a key word that means something. What does rate really mean? Slope. Rate means slope, means derivative, means p prime of x. So keep in mind in calculus we have a lot of synonyms. Rate of change always means slope, which means derivative. So we first need to find p prime of x, which in this case is what? Negative 5x plus 875? And then we want to find the rate that profit is changing when 90 units are sold, so I plug in 90. So again, in this class, when it just comes to basic computations, you can just plug that into your calculator. I don't need anyone to show me negative 5 times 90 plus 875. You can just type it in, and the answer is 425. Let's all interpret that real quick. Anytime it's a derivative, what does this number represent? A slope. So I'm going to put 425 over 1. What are my units from my graph? My x-axis is actually quantity, which is really the number of objects that you're selling. And my y-axis is really profit. So what does this slope represent? This is $425 in profit for every one object that I sell. So at the moment that I sold 90 objects, at that moment, that object earns me $425 in profit. And so this is the definition of marginal profit. This is marginal profit. That's how much profit I got from that object. So once again, if you want marginal anything, marginal revenue, marginal profit, marginal cost, it's just the derivative. And that tells you the marginal profit of that object. So all these words go together. Marginal profit is how much profit I got from selling the 90th object. And that's also telling me the rate that profit is changing when 90 units are sold. At exactly the 90th unit that I sold, I was making $425 in profit per object, which is the marginal profit. It's how much profit I got from selling the 90th object. Okay. Now this next one's a little trickier. It says the rate, so first of all, what are we talking about? Slope or derivative, that profit changes on average when the number of units rises from 90 to 80. I'm sorry, from 90 to 180. Now this is a little different. They're saying find the rate of change of profit on average when the number of units sold goes from 90, which is there, to 180, which is there. So everybody update your graph. This is why a graph is so important. So much of calculus is done on a graph in terms of your ability to understand what the question's even asking. So what does it mean that I want to find the rate that profit changes on average as the number of units rises from 90 to 180? What am I really going to find from this graph, keeping in mind that rate means slope?
The slope between 2 points.
Yeah, the slope between those 2 points. So we're about to find the slope from 90 to 175. So let's jot that down. This coordinate was 90, 50,000. And this coordinate we don't know yet. The coordinate 180, we have to go back and actually find that. What's the profit when x equals 180? You'd have to plug 180 into that whole function, right? Negative 2.5 times 180 squared plus 875 times 180 minus 8,500. That coordinate is 68,000. So I now have the 2 coordinates I'm interested in. Slope from 90, 50,000 to 180, 68,000. And you can all just calculate that slope using the slope formula. Our slope formula would be 68,000 minus 50,000 all over 180 minus 90, which is 18,000 over 90, which is 200. I think 18,000 divided by 9. Yep, 200. Again, 200 over 1. It's a slope. Didn't do anything fancy right there. That was just the slope formula between those 2 coordinates. And so what does that mean? That on average, as I went from 90 units sold to 180 units sold, how much was my profit going up per item? $200. I was getting $200 more per each item that I sold.
So we just put 200 original equation.
Well, this is x1, y1, and x2, y2. So you just do the slope formula.
You got the 68,000 by substituting the
Yes, substituting in and subtracting and doing the slope function. Folks, I realize I only have a couple minutes here, 3 minutes. So the very last one, E, the number of units sold when profit stops increasing and starts decreasing. This is a great question. First of all, do we already know that answer from the graph?
Yes.
How much profit are we making when profit stops increasing and starts decreasing? How much profit are we making? $68,062.50. So we already know the answer. Oh wait, I'm sorry. The number of units sold. Okay, we knew that, 175. The number of units sold when profit stops increasing and starts decreasing is 175. We know that from the graph, and therefore that's cheated. We use the graph to get all the answers, so we know the answer. But how do we do it with calculus? Well, if your profit is no longer increasing and it starts to decrease, what happens to your slope at the very minute that you're not increasing, but before you start decreasing, what's the slope right there? 0. So what they're really asking us to do is set that function, set the derivative, p prime of x, which is negative 5x plus 875, equal to 0, and solve. And remember, this is how you find a minimum or a maximum. You set the derivative equal to 0 and solve for x. Hopefully none of us are going to be too shocked with the answer, which is going to be negative 5x equals negative 875, divide off the negative 5. What do we get? 175, which is exactly what we expected we'd get from the graph. So 175 is the number of objects that you have to sell to be at the maximum. Okay, now, since we're about to leave, I see that I did not finish number 1, 7, and 8, right? 1, 6, 7. Sorry, 1, 6, 7. I didn't do 1, 6, 7. So when you go to do the homework tonight, don't do 1, 6, and 7, right? Because I didn't walk you through it yet. You can try, but don't beat your head up against the wall. And let's just wait until Wednesday when we'll finish 1, 6, and 7. And then also on Wednesday, we will do section 2.6. So let's look here. Yep. So on Wednesday, you'll come back. We'll finish 2.5b, and then we'll start 2.6. Both of these are due next Monday. So you don't have any homework due on Wednesday. But if I were you, I'd go home tonight and do all the problems from 2.5b that you can do. Always do the homework immediately after class because it's fresh in your mind. Also, folks, can I make a request? Y'all are doing great with sending me emails, and I really appreciate that. But I think now would be a good time that we, instead of sending me emails, just post it to the forum. I think that helps everybody. So you notice at the bottom where it says message instructor, instead of clicking message instructor, click post the question to the forum. Because that way you're asking me a question, and when I respond, everybody can see the response, and everybody benefits. And you know, if we had like 10 people email me, then there's going to be 10 publicly available answers with help to everybody. So, you know, at the same time, I realize if you're shy, maybe you don't want to post your question to everybody because you feel silly. But I encourage you, don't feel silly. If you have a question, so do at least 5 other people in the class, and you're the hero asking the question, which is going to get the answer to help everybody. So, everybody, I encourage you to post this question to forum rather than message me. But if you don't feel comfortable, you can still just message me, and that's okay. All right, thanks, folks. I do have office hours right now. Anybody? You can come on over to office hours. Oh, wasn't I going to give you your test? Don't any of you want your test? Yeah. Nobody's pounding on their desk saying, wait a minute, Mr. G, where's my test? Here it is. Diego? Sadia? Efren? Josue? Allison, not here. Aldo? Sila? Bata? Michelle? Sarai? There you are. David? Alexis? Oh, you can go once you have your test, or if you want to stay and ask me questions, that's fine too. You can bring your test to my office hours if you have questions. I'm happy to help you.
So we didn't have any homework in town, right?
Steven?
Alright. You should probably double check.
Lisette? Brandon? Simone? All right, thank you, everybody. And Brandon, I had down an appointment with you today, right? Okay, good. What's that?
We'll just head over to.
Yeah, yeah, I'll be right there. All right, yes, sir. Uh-huh. Yep. Yeah, so the outside function is something to the fifth, so that would become 5x to the fourth.
So final one will calculate all the. So this one is final answer, right?
No, here, let me write this down. So you have here something to the fifth, that's the outside function, and then x plus 1 over x plus 2, that's the inside function. So I'm going to call this outside, that's inside, and then so that just for fun, right next to it, I'm going to write the derivatives, right? So if this is the function itself, then this is the derivative. So here's f of x, here's f prime of x. So the derivative of this would be 5 something to the fourth, and the derivative of this is 1 over x plus 2 squared. So now how does the whole thing work? The chain rule works like this. You take the derivative of the outside function, so the derivative of the outside function is 5 something to the fourth, leaving the inside alone. So I'm going to keep the x plus 1 over x plus 2. Then you multiply by the derivative of just the inside function. So the derivative of that is just that, and 1 over x plus 2 squared. And that's the pure chain rule without doing any simplification.
So I'm still confused with this number. Did I put the same parentheses like I have to put this parentheses?
You still need to put one at the very beginning and one at the very end. Always.
Okay.
Yeah, I would just always do that.
But all the denominator.
Yeah, just only, well, you can put it on the denominator too. That's also a best practice. The best practice, let me see your paper. The best practice is anytime you have a numerator, wrap that whole numerator in parentheses, and whenever you have a denominator, wrap the whole denominator in parentheses. That way, that's going to help you as you type it into the computer. Because when you type it into the computer, those parentheses had better be there, so you might as well do it on your paper as well. Does that make sense?
Yes.